In 1914, a machine the size of a small house bit into the earth at Culebra Cut, Panama. Its steel teeth closed around 40 tons of rock and jungle soil. Steam hissed from its boiler at 150 pounds per square inch. And when that bucket swung over the waiting railcar, it dumped enough material to fill a living room. That single bite took 11 seconds. The men operating these machines worked 12-hour shifts in 95-degree heat, with humidity so thick you could taste the rust in the air. They moved 232 million cubic yards of earth to build the Panama Canal. That's enough dirt to bury Manhattan under 14 feet of soil. But here's what most people don't realize. The machine that made the Panama Canal possible, the steam shovel, was already 80 years old by then. And the excavator you see on construction sites today would be unrecognizable to those operators. It can spin 360 degrees continuously. It can place a pipe with millimeter precision. It can demolish a building in the morning and dig a swimming pool by afternoon. The excavator went from a railroad curiosity to the most versatile machine humanity has ever built. This is how it happened. The story begins in 1835 in Canton, Massachusetts, with a 22-year-old civil engineer named William Smith Otis. Now, Otis wasn't a famous inventor. His cousin Elisha would later become a household name with a safety elevator. But William saw a problem nobody else was solving. Railroad construction in the 1830s was brutal, slow work. Crews of men with pickaxes and shovels moved dirt by hand into horse-drawn carts. A good crew of 20 men could move maybe 100 cubic yards in a full day of back-breaking labor. The Baltimore and Ohio Railroad needed to move millions of cubic yards to lay track across the Appalachian Mountains. Otis designed something radical, a machine mounted on railroad tracks, powered by a steam engine, with a digging bucket on the end of a wooden boom. The bucket could scoop about a cubic yard of earth, swing to the side, and dump into a rail car. The whole operation ran on chains and gears, connected to a small steam boiler that the crew fed with coal and water. Stop and think about that for a second. Before Otis, every canal, every railroad cut, every foundation in human history had been dug by human muscle or animal power. The pyramids were built with rope and sweat. Roman aqueducts were carved by slaves. Then Otis changed the fundamental relationship between humanity and earth. His steam shovel wasn't elegant. The boom was rigid. The machine couldn't rotate more than 180 degrees. It could only dig directly in front of itself. But it could do the work of 50 men. The first Otis steam shovel went to work on the Western Railroad of Massachusetts in 1837, and railroad construction would never be the same. Otis patented his design and licensed it to contractors across the Northeast. The machine spread along the expanding American rail network. But Otis himself wouldn't live to see his invention transform the world. He died in 1839, at just 26 years old, probably from typhoid fever. His patent had only 4 years left to run. After the patent expired in 1843, other manufacturers rushed to build their own versions. The machines grew larger. The boilers grew more powerful. By the 1880s, steam shovels had evolved into industrial monsters. A company called Bucyrus, founded in 1880 in Bucyrus, Ohio, emerged as the dominant manufacturer. Their machines were beasts of iron and steam, weighing 90 tons, with buckets that could grab 5 cubic yards in a single bite. The boilers ran at pressures that would have terrified Otis. The gears and chains were forged from hardened steel that could withstand years of punishment. The Bucyrus steam shovels became the backbone of American expansion. They dug the Chicago Drainage Canal, reversing the flow of the Chicago River to carry sewage away from Lake Michigan. They stripped coal from the hills of Appalachia, feeding the furnaces of American industry. They carved railroad grades through the Rocky Mountains, so connecting the coasts with ribbons of steel. Anywhere America wanted to reshape the earth, Bucyrus was there. But the Panama Canal was their proving ground, the project that would define what mechanized excavation could accomplish. The French had tried first. Ferdinand de Lesseps, the hero of the Suez Canal, arrived in Panama in 1881 with grand ambitions. He planned a sea-level canal, just like Suez. He brought the same techniques: hand labor, small equipment, mule carts. Panama destroyed him. The terrain was nothing like the flat Egyptian desert. The isthmus rose 300 feet above sea level. Rivers flooded unpredictably. The jungle grew back faster than crews could clear it. And then there was disease. Yellow fever and malaria swept through the workforce like scythes. Workers died so fast the French couldn't bury them quickly enough. Bodies were preserved in barrels to await proper burial. Over 9 years, 22,000 workers died. The project went bankrupt in 1889. When the Americans took over in 1904, Chief Engineer John Stevens made a decision that changed everything. He understood that the Panama Project was fundamentally an excavation problem. The mountain had to move, so he ordered 102 Bucyrus steam shovels, the largest fleet ever assembled in one place. These weren't the small machines from Otis's day. Each Bucyrus Type 95 weighed over 90 tons. The bucket could grab 5 cubic yards of earth and rock. The boom was made of riveted steel beams strong enough to lift a locomotive. Steam pressure in the boiler reached 150 pounds per square inch. Each shovel had a crew of 5 men working in conditions that would horrify modern safety inspectors. And the engineer controlled the boom and bucket using a series of levers and foot pedals. The firemen kept the boiler fed with coal, shoveling continuously to maintain pressure. The crane operator managed the swing mechanism. 2 more men maintained the tracks beneath the shovel and cleared debris that could jam the machinery. The heat was staggering. Temperatures inside the shovel cabins exceeded 120 degrees Fahrenheit. The steam boilers radiated heat like furnaces, and the tropical sun beat down without mercy. Men collapsed regularly from heat exhaustion. They drank water by the gallon. They worked anyway because the canal demanded it. At the peak of construction, those 102 steam shovels were removing 2,000 cubic yards per hour from Culebra Cut. They worked in choreographed sequences, each machine filling a train of cars, one then moving aside as the train pulled away and another took its place. Dirt trains ran constantly, hauling spoil to dumping grounds miles away. It was industrial ballet performed with 90-ton dancers. The canal opened in August 1914. It had taken 10 years and $375 million. But more than any single achievement, it proved what mechanized excavation could accomplish when applied at scale. Now, steam shovels had a fundamental problem that limited where they could work. They ran on coal and water. A typical Bucyrus machine consumed 2 tons of coal per shift. You needed supply trains just to keep them fed. You needed water tanks to refill their boilers. The logistics chain was enormous, which meant steam shovels only worked where railroads already existed. Diesel engines changed everything in the 1920s and 30s. Rudolf Diesel's invention had been around since the 1890s, but it took decades for the technology to mature enough for heavy equipment. When it did, suddenly you could run an excavator on liquid fuel stored in a simple tank. No constant shoveling, no water supply. The machines became truly mobile, but these early diesel machines still use cables to operate. The bucket hung from steel cables that ran over pulleys on the boom. You raised and lowered the bucket by winding or releasing cable on drums powered by the diesel engine. You closed the bucket, called a clamshell at the time, by pulling another set of cables that drew the 2 halves together. Cable machines were powerful. Enormously powerful. The Marion 6360, built in 1965 for the Captain Mine in Illinois, weighed 15,000 tons and could lift 300 cubic yards in a single bite. When its boom stretched 215 feet into the sky. It was the largest mobile land machine ever built by human hands. They called it the Captain and used it to strip mine coal, removing entire hilltops to reach the seams beneath. But cables have limits that no amount of engineering could overcome. They stretch under load, they wear from constant friction over pulleys, they eventually snap, sometimes catastrophically. A cable excavator operates with inherent imprecision because there's always slack in the system. There's always a moment of delay between the operator's command and the bucket's response. For moving mountains of earth at mining sites, cables worked fine. Precision didn't matter when you were dumping 300 cubic yards into a pile, but construction needed something different. Contractors needed machines that could dig a trench with vertical walls. Machines that could place a pipe within an inch of specification. Machines that responded instantly to operator input. The real revolution came from France in 1951. A company called Poquelin, run by the Bataille family in a small town called Le Plessis-Belleville, built something entirely new. Instead of cables, they used hydraulic cylinders. Pressurized oil pushing against pistons, connected directly to the boom, arm, and bucket. No cables, no pulleys, no slack. The difference was immediate and profound. A hydraulic excavator responds instantly. When the operator moves a joystick, oil flows through reinforced hoses at 5,000 pounds per square inch. The cylinder extends or retracts within milliseconds. The connection between operator intention and bucket movement becomes direct and precise. The bucket becomes an extension of the operator's hands. Hydraulics also allowed something cables never could achieve. Full rotation. A hydraulic excavator sits on a slewing ring, a massive bearing that allows the upper structure to spin 360 degrees continuously. A cable machine could swing maybe 270 degrees before the cables would tangle and bind. Hydraulics freed the machine to work in any direction without repositioning. An operator could dig a trench, spin around, and load a truck behind without moving the tracks. Poquelin's first hydraulic excavator, the TU, was small by modern standards, maybe 15 tons, but it could do things no cable machine could match. It could dig a trench with perfectly vertical walls. Oh, it could grade a surface flat within centimeters. It could pick up a concrete pipe and place it precisely where the plans demanded. Word spread slowly at first. American manufacturers dismissed hydraulics as a European curiosity, unsuited for serious earth-moving work. The big names in excavation, Bucyrus, Marion, P, and H, kept building cable machines. They dominated the industry for 80 years. Their customers knew cable machines. Their factories were tooled for cable machines. Why change what worked? The Japanese saw it differently. Komatsu, a company founded in 1917 to build mining equipment in rural Ishikawa Prefecture, embraced hydraulics completely. By the 1960s, they were building hydraulic excavators that outperformed anything American manufacturers offered. Their machines were reliable, they were efficient, and above all, thought that they were precise in ways cable machines couldn't match. Caterpillar, the yellow giant of construction equipment, the company whose name had become synonymous with heavy machinery, didn't even enter the hydraulic excavator market until 1972. They'd been selling dozers and loaders and motor graders for decades, watching the excavator revolution happen without them. When they finally jumped in, they were playing catch-up against Japanese companies that had been refining hydraulic systems for 20 years. The American cable shovel manufacturers mostly didn't survive the transition. Bucyrus merged and shrank. Marion faded away. P and H retreated to specialized mining equipment. The hydraulic excavator had become the new standard, and if you couldn't build one, you were finished. Today, the hydraulic excavator is arguably the most versatile machine in existence, and that versatility comes from a deceptively simple innovation called the quick coupler. A quick coupler is a hydraulic mechanism on the end of the excavator's arm that allows an operator to swap attachments in minutes without leaving the cab. 2 hydraulic pins release the current attachment. The arm lifts away, picks up a new tool, and the pins lock into place. The same machine that digs a foundation in the morning can crush concrete at noon and load trucks by afternoon. The list of available attachments is staggering. Standard digging buckets come in dozens of sizes, from 12 inches wide for utility trenches to 72 inches wide for mass excavation. Trenching buckets have narrow profiles and reinforced teeth for cutting through hard soil. Grading buckets have smooth bottoms and no teeth for finishing work. Hydraulic breakers deliver up to 2,000 blows per minute to shatter concrete and rock. A mid-sized breaker hits with 3,000 foot-pounds of force per blow. It can reduce a concrete wall to rubble in minutes. Grapples have hydraulic jaws for grabbing logs, debris, and irregular objects. Demolition shears can cut through steel I-beams like paper, their hardened blades powered by cylinders generating 100 tons of closing force. Augers drill holes for fence posts, utility poles, and pier foundations. Compactors tamp soil in trenches where roller machines can't fit. Magnets separate ferrous metal in scrap yards. Thumbs attach opposite the bucket, allowing the excavator to grip objects like a massive mechanical hand. Count them all, and you'll find more than 50 standard attachment categories, with hundreds of variations within each category. A single excavator can replace an entire fleet of specialized machines. A Komatsu PC200, the best-selling excavator in history, weighs about 20 tons. It costs roughly $150,000 new. Its hydraulic system operates at 4,500 psi. A competent operator can dig a basement, install utilities, grade the lot, load debris into trucks, and place landscaping boulders without ever leaving the cab. One machine, one operator. Work that would have required a dozen specialized crews a century ago. But the excavator has also scaled up in ways William Otis couldn't have imagined. The Liebherr R9800 is a mining excavator built in Colmar, France. It weighs 810 tons. Its bucket holds 47 cubic meters of material, at roughly the volume of a small swimming pool. The machine stands 4 stories tall. Each track is 15 feet wide to distribute the enormous weight over unstable mine floors. The R9800 runs on 2 diesel engines producing 4,000 horsepower combined. It burns 250 gallons of fuel per hour at full load. It costs approximately $11 million. Mining companies buy them because a single R9800 can load a 400-ton haul truck in 4 passes. 4 passes. Maybe 2 minutes of work. That efficiency, multiplied across 24 hours of operation, across 365 days of the year, is worth tens of millions in productivity. At the other extreme, the mini-excavator revolution is reshaping construction in cities and suburbs where space is precious. Kubota's KX040 weighs less than 10,000 pounds. It's narrow enough to fit through a standard backyard gate. Its tail swings within the width of the tracks, meaning it can spin in tight spaces without hitting walls or fences. An operator can load it on a trailer behind a pickup truck, drive to a job site, and be digging within minutes of arrival. These machines have become the Swiss Army knives of small contractors, landscapers, plumbers, and increasingly homeowners who rent them for weekend projects. Need to dig a koi pond? Mini excavator. Install a French drain? Mini excavator. Remove a tree stump? Mini excavator with a thumb attachment. The mini excavator market exceeds $10 billion annually and grows faster than any other segment of the industry. Why? Because they solve the last mile problem of construction. You can't drive a 20-ton excavator into a residential backyard. The machine would sink into the lawn, crush the sidewalk, and probably collapse the sewer line underneath. But a mini excavator slips through the gate, does the work, and disappears without a trace. The future is already arriving on job sites around the world. Electric excavators now operate on construction sites across Europe and Asia. Volvo's ECR25 electric runs on lithium-ion batteries that provide about 5 hours of typical operation. No diesel fumes. Noise levels 50% lower than conventional machines. They can work inside buildings, in enclosed spaces, in urban areas where emissions regulations prohibit diesel equipment. Hospital additions, museum renovations, and basement excavations in historic districts that would have been impossible with diesel machines are now routine with electric. Autonomous excavators are being tested at mining sites in Australia and Canada. The machines use GPS, accurate to centimeter precision, LiDAR sensors that map their surroundings in real time, and machine learning algorithms that optimize digging patterns. A control room in Perth can manage excavators working 800 miles away in the Pilbara Desert. The machines dig and load around the clock, stopping only for maintenance. The operator's role shifts from controlling the machine to supervising the fleet. Adit, think about the distance we've traveled. William Otis built a steam-powered contraption that could scoop earth and swing it aside. It was crude and limited and absolutely revolutionary. His machine could move a cubic yard in about a minute. It required a crew of men. It ran on coal and water. It could only work where railroad tracks already existed. Today, a Liebherr R 9800 moves 47 cubic meters in a single pass. That's roughly 50 cubic yards in 8 seconds. The same volume that would have taken Otis's machine an hour. One operator controls it from an air-conditioned cab with joysticks and computer screens showing exactly where the bucket is, relative to the planned excavation. But the excavator's true legacy isn't measured in cubic yards per hour. It's measured in everything those cubic yards made possible. Every foundation beneath every building in the modern world was dug by excavators. Every sewer line, every water main, every fiber optic cable, every gas pipeline connects our cities through trenches cut by these machines. Every mine that produces the copper for our wires, the iron for our steel, and the rare earths for our phones depends on excavators to move the overburden and reach the ore. The Romans built their empire with slave labor and hand tools. We built ours with hydraulic fluid and diesel engines. And now we're building the next one with batteries and algorithms. If you watch this far, you understand why the excavator matters more than almost any machine ever invented. Hit subscribe because next week we're covering the machine that works alongside it on every major project.